Alright, I want to give you some information about how to handle the determination of absolute zero lab. Now the first thing I think you should do is read through the background of the lab. Now I know a lot of it is stuff that you probably won't understand, but that's okay. There's certain points they make that I think are important, and one of those important things is that as volume goes down, temperature goes down, or as temperature goes down, volume goes down. And we're talking about gases here. So what we're saying is that at high temperatures, the gases will expand. At low temperatures, they contract. And I think that that's something that we all know about. We know that from tire pressures. We know on cold days, tire pressure goes down, and that's the day that people line up at the gas station to get their tires filled. So we see that all the time, and what we're going to do is we're going to use that relationship in order to figure out what the temperature is of absolute zero, because at that temperature we're assuming that the volume of the gas will go down to zero as well. So by doing a graph of volume versus temperature, and knowing that at high temperatures we're going to have high volumes, at low temperatures we're going to have low volumes, as we go down to zero on the volume, the temperature will approach what we believe to be absolute zero, the lowest possible temperature that we can get. Now the only thing you really need to worry about math-wise here is how to get the temperature, and we can do that by taking the intercept over the slope of a graph of total volume versus temperature. Alright, so let's see how we might do that. The first thing we're going to do is just follow the procedure, and it says we need to take a 150 ml Erlenmeyer flask there. And then what we can do is we can take a pressure gauge, and from the instrument says the pressure gauge, stick that in, and then we fill it with some kind of gas up to 1.50 atmospheres of pressure. So I'm just going to take a material here. Let's see. We'll do methane, and we'll stick it in. And it says we need add up to 10.0 atmospheres. We're going to put 1.50 because that's what it says to do in the lab, and hit OK. And you'll notice that the pressure gauge, if you zoom in on it, says 1.50 atmospheres. So that's good. The next thing we need to do is take a gas syringe and drop it onto the Erlenmeyer flask. Here it is. And we stick this in. Now, what I want you to do is watch the volume on the gas syringe as we do this. In fact, I'm going to put this back for a second. We'll zoom in and do this. Okay, watch what happens to the syringe when I put it on the Erlenmeyer flask. You'll notice that what happens is the pressure equalizes. So we still have just as much gas in here as we always had, but some of the gas will stay in the flask and some of it will flow into the syringe, and that's what's happened. And you can see now the volume of the syringe is 75.0 mils. Next thing we do is we take a thermometer, stick that on, and that'll measure the temperature. So here's what we know. At 21.5 degrees Celsius, the volume of the gas is 75.0 milliliters in the syringe. So I'm going to go ahead and I'm going to write that down in my notes over here. .5, the volume, I think we said was 75. Let me check on it again. 75.0. Now you'll notice I've got a third. Sorry about that, it's a bit finicky. It's a bit slow right now. Give me a second. Alright, this again. There, that's better. 75.0 mils. Now the total volume of the gas is going to be, let's go take a look at this, because we need to measure the total volume of what's going on, and the volume of the flask is given as 150 mils, and then you've got to add in the volume of the gas in the syringe. So the total volume, which is what we're going to measure, will be 225 mils. Whoops, we don't need the mils here, it's already in the table. So it'll be 225 mils for the total volume. Alright, so you'll see that we have to take the constant temperature bath from the instrument shelf, and you can see that it's currently at 21.5 degrees Celsius. Now we have to set the temperature of the constant temperature bath to 100.0 degrees. So just keep on clicking it until you get to 100. There we go. So it's at 100. And then what we do is we place the Erlenmeyer flask in the constant temperature bath. Now what's going to happen, of course, is that the flask is going to get heated and the gas is going to get heated. But here's the thing. The gas will only ever reach the temperature of the constant temperature bath. It's not going to go any higher than 100. And that's it. But you'll see it goes up, keeps on going, keeps on going. So I'm just waiting patiently for it to get to 100 degrees. It's at 99.4. Keep going. Alright, so now it's reached 100. It's not going to go any higher than that. But take a look at the gas in the syringe now. Because the gas is hotter in the flask, we expected it to expand, and it has, and it expanded to 135.0 mils. So now that allows us to get our data for that point. And you can see that the total volume then would be 135 plus 150, which would be 285 mils. Right, so that's how we're going to get all of these points. Now you're going to find a whole bunch of other temperatures and volumes as well, but always just mouse over the gas in the syringe. You'll be able to get what the volume of that is going to be. Now it's telling you 0.0, 21.5, 30.0, 40.0, 50.0, and 60.0 and 80.0. And you can get all those temperatures just by clicking on the constant temperature bath, and it will give you all of those different temperatures. So once you've got that, you can go back and you can start doing a little bit of the math. Now I've marked down these temperatures here and I've got the total volumes. So let's go back to the procedure now. So exit out of here. Sorry, go back to the lab report. As I said, you're going to have a whole lot of other points to put on here. But look what it's asking you to do. It says create and save a graph of the recorded data with the temperature in degrees Celsius on the x-axis and total volume in milliliters on the y-axis. It says remember that the total volume includes both the volume of the flask and the volume in the syringe. So that's why I found that total volume. And you do this by clicking on the graph icon, and then you can create your graph. Now I'm only going to have 2 points on mine because that's all I did. Now here's what it said to do. It said that we need to find the, let me close that down here. It said that what we needed to do was put the degree Celsius on the x-axis and the volume on the y-axis. Now it's important that we obey exactly what this says, otherwise our graph won't work out properly. Alright, so temperature on the x-axis and volume on the y-axis. So we've got 21.5 and 225. Remember that's the total volume. That's the gas in the syringe plus the volume of the Erlenmeyer flask. And the other one, 100.0 degrees, and I think it says 285, right? Yeah, 285. Now you'll have a whole lot more points, but we'll go ahead and do this anyway. And you can see I've got a graph here that's got the points on it. Now if I click on show trend line, here's what's going to happen. It's going to show me the slope and it's going to show me the intercept. Now as it states here, it even says it here, it was in the background as well, that the absolute zero temperature will be found by taking the negative value of the intercept divided by the slope, and then we'll be able to figure out exactly what absolute zero is based upon that. I'm going to leave that to you. I think you can handle that. The percent error, you've got T experimental minus T accepted over T accepted. It tells you even here what the accepted value of absolute zero is, so you can just do the math on that and figure out your percent error. So your value should be pretty close to minus 273. It might not be exact, it probably won't be exact, and there'll be a small percent error that you're going to see here. Now, as for the conclusion questions, I am pretty confident that you can get at least half decent answers to those if you read through the background in the lab. So just reading the background portion in the lab portion will allow you to get a lot of those answers. Alright, so that's pretty much all I wanted to do here. Just make sure also when you do the graph you put a title on, you put the axes and you title the axes and everything. I didn't do that because I just wanted to give you a rough idea of how to get the math done for this particular lab.